Hello everyone, welcome to FSI 305 Scaling Security Guardrail Development with the AWS CDK. Joining me today as presenters are Michael Lysaw, Richard Julian, and Michael Neal, Senior Vice Presidents with Cloud Engineering at Citi. In this session, they'll take you through their journey to resolve security, development, and operational challenges such as the continuous changing threat environment, how to enable secure development across business units with their unique workloads, and scaling pipeline complexity for integration and development of code and infrastructure supporting security guardrails. So I'm going to hand it over to Michael.
Thanks, Freddie. Hello, everyone. I'm Michael Lysaw, Senior Vice President of Cloud Security Engineering at Citi. And together with Richard Julian, who is also here with me today, I lead Cloud Security Controls Engineering at Citibank. So first off, I just want to give a shout out to the full team involved in what we're going to present today. We're representing a really talented DevSecOps team of cloud security engineers at Citi. We're spread out all over the US, from West Coast all the way to East Coast, and a short hop over to Ireland, where I'm currently based. We're a team of generalists, and it's really worth stressing that we consider ourselves developers that do security rather than a security team that do software development. So right now, our primary focus as a team is on developing controls to secure Citi's infrastructure and platforms in AWS, where these controls automatically assess and enforce security policies in Citi's AWS environments, including configuration mishaps, and where the ultimate goal of these guardrails, that we often call these controls, is to keep Citi's infrastructure and applications secure and at the same time maintain or even increase developer velocity. So these controls or guardrails are either detective, auto-responsive, or preventative in nature. But today we're going to focus in on only the detective and auto-responsive controls. Now, before I give an overview of what a standard guardrail looks like, let's first take a step back to get a feel of how the use cases and requirements of a standard auto-responsive control get set. So in Citi, a solution architecture is proposed through a formal process, where at an early stage of that process, a team of threat modelers working closely with other security teams assess the architecture and identify a list of threats in order to mitigate those threats. Our engineering team then work closely with that same set of stakeholders to design and engineer the security controls that mitigate those threats. So a fairly classic example of a threat, and one of real concern across all of Citi's AWS environments, is the disclosure of confidential data via a public S3 bucket. So right now, we don't want to ever see a public S3 bucket in any account, any AWS account owned by Citi. Now, it should be stated that we have implemented multiple controls that help to prevent an S3 bucket from appearing as public in any Citi-owned AWS account in the first place. But adopting a layered approach to security, we're also focused on developing mitigating auto-responsive controls that, in the case of a public S3 bucket, would, for example, re-enable preventative controls that had been unintentionally or even intentionally or maliciously disabled, so as to re-enable those preventative controls, or in a worst case scenario, would trigger off an S3 bucket actually being made public, and so in that case would subsequently reconfigure the access controls on the bucket so that the S3 bucket is set back to private. Now, for threats that are scored as high or priority within Citi, our focus is on ensuring that we engineer controls that can alert and auto-remediate with as low latency as possible. So if an S3 bucket gets set to public, or for example, an internet gateway gets deployed in an account that it shouldn't get deployed into, we want to ensure that an alert gets sent to relevant security teams as quickly as possible, as well as ensure that we have an auto-responsive control that deletes an internet gateway, or in the case of a public S3 bucket, reverts the access controls back to private on that bucket super fast. And it's this low latency requirement that has motivated us to design our event-driven guardrail system with CloudTrail, EventBridge, and Lambda as its core components, with a combination of these services allowing us to engineer auto-responsive controls that can auto-remediate on the order of seconds. So let's take a look at a standard guardrail. So what we're seeing in front of us are two 12-digit AWS accounts. On the right side, we have a central or hub security monitoring account where the vast majority of our event-driven security platform exists. And on the left-hand side, we have a spoke account that from a security baseline perspective is representative of a standard tenant account within City, i.e. every other account but the security monitoring account in the AWS organization. And what I'm going to do now is bring you on a very short helicopter tour of how a guardrail works, following the sequence of numbers that you see in front of you in the schematic. So first off, at point 1, you can see an API call is made by an attacker within the spoke account that reflects either malicious activity or a configuration mishap. So in this example, you can see that the create internet API, internet gateway API is called. But it could also, for example, be the updating of a bucket policy to allow public access to the bucket, or the disablement of S3 public access block controls at the bucket or account level. The API call made is recorded by CloudTrail within the spoke account, with the default integration between CloudTrail and EventBridge resulting in that recorded CloudTrail event surfacing as an EventBridge event on the event bus within the spoke account. And through a coarse-grained event rule deployed to the spoke account as part of a security baseline, that event is forwarded to the event bus in the hub security monitoring account that you see on the right-hand side. So now, following the sequence into the hub account on the right-hand side, we can see a fine-grained EventBridge rule filters for specific API calls, and if invoked, triggers a Lambda function. And this Lambda function invoked by the EventBridge rule evaluates the event payload and determines important information on the affected resources, including the spoke account that's being impacted. And then in the case of an auto-responsive guardrail, assumes a cross-account role into the affected account to remediate the affected resources. In this case, it would be the deletion of an internet gateway. In the case of a public S3 bucket, it would be modification of the access controls on the bucket to revert the access controls back to private. The Lambda function then subsequently creates a resultant security message for security teams, which gets forwarded to those same teams via an SNS topic and SIEM tooling that you can see in the schematic. Now, one of the challenges we face as a small team is the increasing demand within City for using more AWS services and the need to develop new guardrails focused on those services. So far, we've developed and deployed to production hundreds of event-driven detective and auto-responsive controls. But we're a small team, and naturally we're looking for ways to better scale the development of an ever-increasing number of guardrails due to City's appetite for more and more AWS services. Now, in our green days of developing guardrails, we were pretty excited by the fact that we were defining our guardrails through infrastructure as code using what we thought was a standard CloudFormation template for a fairly standard or fixed guardrail pattern. And we even went as far to develop an initial version of a Python library of helper functions for some of the common patterns we were seeing across those early guardrails. And we figured that if we simply copy this CloudFormation template from guardrail repo to guardrail repo, everything would work out rosy, and we could scale guardrail development across our team and across a growing number of control requirements. So what could possibly go wrong with this approach? I'm now going to hand you over to Richard Julian, my colleague, who's going to talk about some of the challenges we faced into as a team with this early approach to our controls development. So over to you, Rich.
Thank you, Michael. My name is Richard Julian. I'm also leading the cloud security engineering team at City with Michael Lysat. And I get the ominous joy of taking a what could go wrong introduction and walking you through the journey that we started with these guardrails. and really kind of showing you our first revolution for how we were building and deploying the system into our environment. And so, like Michael said, we started off with CloudFormation, and CloudFormation makes a lot of sense for developers in AWS. It provides the ability to manage your infrastructure in stacks, and it fits really nicely inside of SDLC pipelines. And it worked for us. For the first 10 to 15 or so guardrails, it was wonderful. We could develop rather quickly, and we could, easily build new controls that fit our security needs. But as Michael alluded to, as more and more requests came in, and our way of building more and more guardrails was by copying the repository over, we ran into some issues. And so my goal in this section is to really kind of take you through what sort of pitfalls we ran into, how we recognized those pitfalls, and how we moved forward. And so with that, I'm going to start with talking about how we spiraled our complexity with increasing number of files. So our developers at City are exactly what you want in DevSecOps engineers. They're lazy and they have a habit to automate the boring work that we give them. And so what ultimately happened in our situation is that our developers added in a variety of test scripts, build tools, and configuration management settings that we could ultimately use to make our lives easier. This really was an act of benefit for our team. We wanted to make our lives, our jobs faster and our lives easier. And ultimately, the files that we added to our repository came from a good place. What you see on the screen here in the center is a snapshot of what a directory tree looked like for a given guardrail. It's really important to note in this case that there's 88 files that are listed out there in front of you. And for the purposes of understanding what a guardrail does, only 2 of those files mattered. And one of them was a CloudFormation template that told you what an EventBridge event rule looked like. And the other was a Lambda that kind of outlined the business logic that we would look for certain security policies. And so what we ultimately found was that when we would have engineers come in and look at our code, they would be looking at these 88 files and they would have to take the time to understand which files mattered to edit and which didn't. As an example of that, you'll see on the right a library file that we used in our Lambdas that would ultimately save our developers time from having to rewrite the same functions that had been previously used in other guardrails. This is a great idea and something that should be encouraged for working with Lambdas. However, as we added in these files, we ran into a situation that we couldn't keep track of exactly which version of this file was in a given guardrail. And more importantly, we couldn't even tell whether or not it was used within a given guardrail. So we would just have more additive files as time went on. Additionally, we would increase the size of our files. And this was another area where, as we couldn't understand what was going on inside of the files, we would only be able to add content. We would never be able to edit or remove content. And this happens as requirements and customizations grew for different guardrails. Our only method was basically extending existing code, never taking away. And so I have a great example of this in the makefile on the screen. This makefile started really innocently in our world. It was about 50 lines long. It included a couple commands, and it really was focused on, just taking some of our build jobs and making them easier. By the end of this revolution of our guardrails, this file had ballooned to be over 500 lines. It included over 14 different commands and about 50 configuration items. It even had a second file that brought in even more environment variables to this makefile. And that spelled a nightmare. It was the talk of legends on our team, ultimately. And what would happen is we couldn't tell what we could edit without having something break in the pipeline, or worse, break in a deployed guardrail and ultimately sabotage our security effort. And so this gets to a major problem that we realized rather quickly. It was puzzling for outsiders to really look at our code. And this manifested in 2 ways primarily. The first and quickest to be apparent was, as new developers came on board, it would take longer and longer and longer for them to understand and contribute to our guardrail system. a very talented engineer would look at our code base and have to spend weeks understanding what mattered and what didn't. And ultimately, they would spend months to understand the contextual parts of the extra files that we had in our system. Additionally, when it came to auditing our code and really being able to explain to our stakeholders what we were doing, that was more and more of a challenge. And this is really important. These are security controls. They're what we do to say how we secure the AWS platform. And if we can't get through and comprehend what our code is doing, it actually poses a security risk for us as engineers. And so this leads us to what we call the breaking point. In our world, as we started developing more and more guardrails, of course we had to go through and do simple bug fixes or tweaks or stylistic improvements. And this was really painful. Experienced engineers on our team would have to spend days, if not weeks, looking through historic guardrails, understanding at what point did they come into our existence and what files they would ultimately have to change in order to get the change implemented to fix these bugs. That was problematic. Where things really hit a wall, though, was when we were faced with a systemic change. When we were asked to change something that was across every single guardrail, we realized that we had really very few options. What we could do is we could take all of our guardrails and bring them all to one consistent point and start editing them and bringing them into this new infrastructure. But that would be a massive undertaking for our team. And ultimately, we realized that going forward, we would just get into the same situation where drift would happen. We'd add in more complexity, and we'd have to go back and redo this every so often. So it was convenient that this systemic change faced us at a time when our management was looking at us for the next approach. They came to us and had heard about our change problems that we were looking at with the existing guardrails, and also challenged us with the idea that the work that we were giving them was incredibly useful. We were providing rich metrics for security events inside of our environment, and we were providing really great contextual alerting. So they loved what we were building, but they knew that as our use cases at City grew, we needed to expand this beyond our small team of 10 engineers. We needed to allow outside stakeholders to build their own security policies that matched their custom needs for their applications and their infrastructure. And so we were going to be ultimately taking that infrastructure, that core functionality, managing it ourselves and providing it to these outside teams. We would give them the ability to customize our use case so that they could, contribute back to our infrastructure and satisfy whatever security controls they needed to have in place. And so that led really well into looking at the CDK. A number of us on the team had, outside of work, messed with the CDK and used it in varying capacities, whether in previous jobs or in hobby projects. But we realized that we as a team really preferred working in programming languages. A number of us enjoyed Python, and a number of us enjoyed working in JavaScript. And so we really loved the idea from the CDK that we could use our favorite programming languages and develop our infrastructure as if we were developing software. Our management also loved this too, because we were able to take the same requirements that we have for software, such as unit testing, and put it forward for our infrastructure and finally show within a pipeline that we could actually control for changes in our code. Additionally, we knew that one of our requirements was vending out our code to external actors. And that is where we really loved the idea of the SDLC complexity that CDK provided, and we could really build an asset and distribute it to external teams. And so with that, I'm going to hand you over to Michael Neal, who's going to take you from how we initially started with the CDK and brought our current system into use with the CDK, and then took the features and benefits of the CDK and brought us into a place where the complexity to develop a guardrail and to understand what a guardrail did was significantly handled. So with that, take it away, Michael Neal.
All right, thank you, Richard. My name is Michael Neal, and I am a security engineer at City. So as Richard mentioned, switching to the AWS CDK allowed us to stop treating each of these guardrails as one-off projects and start to treat it as a product. And with any product, we follow a typical software development lifecycle of build, test, release, and validate. It allowed us to do things like simplify and remove configuration of code. We had a lot of boilerplate to do things like validating CloudFormation files or handling deployments and injecting those parameters whenever we needed to run tests. Lots of other files ended up in there, as Richard mentioned, to do other sorts of operations, and many of them were handled by default just simply by switching to the CDK. It also allows us to test our infrastructure as code completely separate from the guardrail lifecycle. And as mentioned again, this is mostly a security issue. We had this huge repository for each guardrail, and it had 88 files and thousands of lines, and it's hard to audit all of that. And one of the most important pieces to us is the infrastructure. And when the infrastructure gets copied around from project to project, it's hard to tell if it had mutated or not whenever it was copied, or which project it was copied from. If you'd copied the infrastructure from an older project, it may not have the latest changes that were required, and these CloudFormation templates would be hundreds of lines long. So in a pull request, that meant that a reviewer had to go through and look at each of those lines of that CloudFormation to make sure that it was valid or that nothing else had been introduced. So we wanted to be able to protect against infrastructure changes that reduced our security, and we also wanted just to simplify the review process and get controls out faster. By moving the infrastructure into this separate product, we're able to test it separately, ensure that the infrastructure is secure and that it follows best practices, and the only thing that ends up within a software engineer, within their pull request, is the package version within their manifest file. So at this point now, the pull requests have a single line, and it says what version of the infrastructure that they're pulling in, and that's in part because we're able to move it off into a package manager. So a simple npm install or a pip install, or however it is that you're distributing your CDK application. Now I'm going to jump into a demo that shows the first revolution of our guardrail changes using the CDK.
This is an abstracted version of a guardrail that points out all the best practices that we've learned while using the CDK. What you're seeing right now is a cdk.json. Every boilerplate CDK application has this file inside of it. It has an app property, and the app property tells the CDK what to execute whenever we run any of the CDK commands. In this case, we're running npx tsnode bin control.ts. If you're not familiar with TypeScript or Node.js, that's not a problem. The CDK is available in multiple languages, and I'll do my best to explain what's going on here. npx is a tool to tell us to run a local version of a program. In this case, we're executing tsnode. The examples have been written in TypeScript, and we need to convert TypeScript into JavaScript. tsnode is a tool that is going to handle that for us. Finally, we're going to execute the control.ts file. Inside of control.ts, we've imported the CDK library. We've also imported the stack that is defined in a different file of the same repository. The stack extends the CDK core stack. That is a common pattern. It's the main way that you interface with a CDK application. We also define some parameters for that stack, the environment, and a name. Our guardrails are going to be deployed into multiple accounts in multiple regions. The CDK recommends that we use environment variables to set any of these parameters. Traditionally, we would use CloudFormation parameters to define these. However, in an imperative programming language, we can use environment variables. We set the account from the environment. And last thing is we set the name of the guardrail. Each guardrail needs to have a unique name. If that name is not set, we've also set a default value. The control stack is defined within the same repository. On line 11, you can see that the control stack extends the CDK stack, as I mentioned earlier. The CDK stack extends another class called a construct. Most things in CDK, and certainly all the resources that you would normally find in a CloudFormation template, are defined as constructs in the CDK. The CDK allows you to extend those constructs, like in this case here. We're extending the CDK stack. Additionally, we can extend individual resources, and we can even use constructs to define multiple or new resources. On line 24, we have a control resource that extends the CDK core construct. It takes a rule that's been defined as well as a function name that we pass from parameters in the app definition. The control resource is going to create a Lambda function, set up the event rule to trigger the Lambda, and finally to provision a destination for any of those messages that the Lambda receives. If we jump inside the control resource, you might notice that it's defined with a completely separate repository. This is the guardrail repository. This is the application where we're keeping all of our infrastructure. In here, we define the control resource, which extends the core CDK construct. Inside of this resource, we're defining the Lambda function, ingesting the parameters that were passed from the other project. We're also adding an environment variable to the Lambda function. This demonstrates some of the extra configuration you might have in your resource. At the end, we're adding the event target so that the event rule matches, it will trigger the Lambda. In addition, IAM rules and other resources will be created automatically for us by the CDK. Let's jump back into the stack and look at the event. The guardrail engineer is really only concerned about two files in this application. The event rule, defined here, which matches some event in CloudTrail. That's only one part of the file the engineer needs to modify. The Lambda function is the other file an engineer is going to need to work with in this application. Here, we have a fairly trivial example of a guardrail handler. In this case, the handler is not really doing anything except returning a value. In the case of a remedial control, it would need to do quite a bit more work. Even in detective controls, you may need to take additional actions whenever you've actually received an event. I'm going to synthesize the CDK stack into CloudFormation and the Lambda package. NPX runs the local version of CDK. We're going to produce the output into a local directory. The Lambda function has been packaged as a CDK asset. The CDK has converted the TypeScript automatically into JavaScript, and the template has been created with our event rule in it. The event rule defined earlier within the CloudFormation stack has actually shown up in the synthesized CloudFormation. To show you a bit more of the power of the CDK, let's go back and take a look at the event rule. If I were to remove the event pattern and save the file and then execute the CDK command again, we're going to get an error. Either event pattern or schedule must be defined. The linter doesn't give us any feedback here. It doesn't know that event pattern or schedule can be defined. Typically, what would happen is that an engineer would deploy the stack into AWS. After a few minutes, the stack would fail, and that's how the engineer gets the feedback. With the CDK, all that validation is done locally, and the feedback is rapid. That's how we ended up with a bunch of files previously. We would write files to do things like call the AWS CloudFormation validate template function. That way, engineers didn't have to wait for the stack to fail before they know if the stack was valid or not. However, that method still requires a network call, and it means that you have to remember the command. In this case, it's all handled for you automatically by the CDK and without any network calls.
You can see we were able to reduce the complexity of our guardrail quite a bit. Unfortunately, it also added a bunch of new requirements. The team using the infrastructure, let's say they'd chosen to use TypeScript to write all of that infrastructure as code, and the controls engineers wanted to use Python. So the way the CDK handles this is they have a tool called JSII, and JSII will take the TypeScript that is written for the CDK and convert it into other languages. And since we're able to use those multiple languages, that is something that the infrastructure team would be able to do, is use JSII and write in TypeScript. But if the infrastructure team had chosen any of the other languages like Python or Java, they wouldn't be able to do the same. So now you're forcing the infrastructure team to learn TypeScript in order to produce multiple other variants that other infrastructure teams, or that the guardrail engineers teams rather, could use, or you're forcing that extra complexity on the team to use JSII. We want to increase adoption, and so requiring these specific languages is not a good way to do that, right? We want to be able to abstract the CDK out. We want infrastructure teams to be able to use the tools that they want. So if we wanted to write the CDK in TypeScript, or we wanted to write the CDK in Python, we should be able to do that. As well, the guardrail engineers or any of the engineers adopting this product want to be able to use the languages that they're used to as well. The AWS CDK is just an implementation detail. Really, the controls engineers, they only care about those two files, the event file, the event pattern, and the Lambda function itself. Since the CDK is an implementation detail, it should mean that we can abstract the CDK away entirely. In the previous example, we still had the lib and the bin folder, and we had the cdk.json, as well as CDK dependencies within inside of the manifest file. None of those are important to the guardrail engineers implementing the business logic. Their primary concern is that a threat comes in from the threat modeling team, they can write an event to broadly match that pattern, and that they can write a Lambda to do additional detective lookups or even remediate the issue as soon as it's found. And lastly, one of the other things not really mentioned is that we want to reduce the environmental configuration. CDK best practice is to use the environment variables to configure the application, but as controls start to get more complex or we introduce new patterns, those configurations become difficult to manage over time. By using environment variables, it's also difficult to audit in a pipeline. Imagine that you forget to log within your pipeline the environment variables that are being set with the application, and now you've rolled the application several times. It's difficult to go back and know what version of the environment or what parameters were used at any given time should you go back and audit and find that maybe there was a bug in the past. Additionally, if you have a new engineer onboarding and they need to go in and update that control, they would have to know what all those environment variables are. Now, a best practice would be to document what the configuration is and to put all that into a README and have the engineer copy that down, but that doesn't always happen. We want something that's self-documenting, and we want to reduce the friction to writing a control. What we need to do is shift the complexity. So if we go to the CDK best practices documentation and we scroll all the way to the bottom, at this point you got to zoom in pretty far, and you can see that they do give you some help. It says start simple and add complexity only when you need it. And that's exactly what we're going to do. So at this point I'm going to jump into another demo that shows you the second revolution of the controls with the CDK abstracted away.
Here we have a more complex example. We've completely abstracted away the CDK in this guardrail. In fact, if you look, there is no cdk.json at all, no lib, and no bin folder anymore to define a stack or import constructs. If we look at the manifest file, the package.json, there is no reference to the CDK at all. The only dependency that we have is our own guardrail package listed on line 22 of the development dependencies. In this case, it is installed from a local directory, but it would be in a package manager in production. The only remaining concern for the guardrail engineers is now the business logic. The event rule is inside of event.yaml. This file is called a template partial. We're going to use it by importing it into our CDK guardrail application whenever we deploy this guardrail. This is a fully qualified CloudFormation template. We can validate it, and one added benefit based on how we've built controls up to this point is that we can take our existing CloudFormation and copy the rule and paste it into this file. That reduces the effort for engineers to adopt this pattern. We have another file, control.yaml. This file isn't necessarily required, although we do need a way to configure our application now. This replaces the environment variables that are hard to audit in pipelines and are not self-documenting. The format you see here is just a suggestion, but we can validate it and we can version it. And we can ensure that different parameters don't conflict. For example, in the future, if we have several different patterns of guardrail that can be deployed, they may have conflicting configurations that we can catch when parsing this file. We still have our Lambda package. This Lambda is the exact same as the Lambda in the other basic example. This Lambda is trivial, and something for a remedial control would need to be much more complicated. But for the purposes of the demo, it will suffice. We've now reduced our guardrail down to 3 total files our engineers know or care about. We have the Lambda, the event.yaml, and the control.yaml. Additionally, in this guardrail, there are unit tests for the Lambda and integration tests that you would want to perform after deployment. These are files that we can't abstract to the CDK. Everything else has been moved off to the guardrail package that has a separate software development lifecycle. We can synthesize the stack just like we did in the basic example. This time, we call npx guardrail instead of npx CDK. That's because the CDK continues to be an implementation detail only. We have the ability to remove, enhance, or augment the CDK at any time. We could even choose to replace the CDK with AWS SAM, serverless, CDKTF, or any other tool that we felt met our needs better in the future. Inside the dist folder, our application has packaged the index.ts into a JavaScript file, just like it did previously. It also created the control stack and imported the event pattern exactly as we expected. In addition to importing the CloudFormation template, we can also do validation on the event pattern like we did previously in the basic example. We can edit and remove the event pattern and run npx guardrail again. When it synthesizes the stack, it gives us back the same error we received previously. Either event pattern or schedule must be defined. In this example, there are 3 additional errors here. We're requiring source, detail, and detail type. We've extended the CDK rule in this case to add additional validation. Extending the event rule is something we could have done previously in the basic example. However, you'll see whenever it's implemented that making those changes in the basic example would be more difficult. In the guardrail package is the application where we've actually written the majority of the infrastructure as code. This is the only CDK application or infrastructure we are concerned with now. In the manifest file, we have our CDK dependencies, as well as the JSON schema that extended the validation that we just showed. Inside of the guardrail.ts file is the same boilerplate application that we saw previously in the basic example with a minor change. This time, instead of configuring our entire application using the environment variables, we passed in a single parameter called config. Config is going to load any parameters that the guardrail engineer needs to define within their application. This package also contains a stack, and it's very similar to the one that was in the basic example we saw earlier. Only now, we're accepting the configuration from our local application, which has loaded and validated the control using the config class. The config class is hypothetical, and you would need to implement that separately. In the constructor of the stack, we validate the event rule. Only if it's valid do we create the node function and continue adding resources like the basic example. At the end, we add the event target. By handling validation early, we're able to fail fast and return clean error messages to the engineers about their stack failures. In the basic example, if we had the stack defined in our guardrail and later on decided that we needed to add this validation step or to handle the validations better, we would have to go and modify each guardrail, and we have hundreds of them. By centralizing the stack and the app, we're able to make quality of life changes for controls engineers by handling validations centrally. All they need to do is upgrade to the latest version to get these changes. Previously, they would have had to copy their own pre-validated rule into each of the stacks and each of the guardrails. We've extended the CDK event rule construct and added a static method to ingest the guardrail event pattern and return a new instance of the control rule with extended validation. The additional validation is shown on line 51. This validate rule method is called at the beginning of our stack. However, since our control rule also extends the CDK events rule, we can call CDK's own built-in validation rule as well. We call the internal validation rule first, and then append our JSON schema validation to the rest of the CDK findings. JSON schema is a library used to validate rules internally with the CDK. By using the JSON schema here, we've extended it and keep the same format without much effort. JSON schema is also available in multiple languages.
As you can see, we've abstracted away the CDK entirely. There's no more mention of anything CDK specific within an individual guardrail. But it wasn't all roses getting to this point. The CDK did have some issues as we used it over time, and we have some learnings that we can share. The first off is that experimental changes mean breaking changes, or sometimes constructs go entirely missing. It's best not to use these constructs within production, and over time the CDK has gotten more mature and fewer of these constructs are experimental. But watch out for experimental constructs. They're great to test, but probably not a good idea to release into production. Another point is that the functionality goes far beyond CloudFormation. Now, this is really good. For example, in the Lambda function that was showed in the demo, if you touch the log retention policy at all, it will pull a custom resource into your account. Now, that custom resource tackles a real problem that CloudFormation can't solve, and that is that it handles log retention for your Lambda. So let's say we deploy a guardrail, and later we find that we need to pull the guardrail or remove the guardrail for some period of time. If we delete that, we have to either retain the logs for auditing or compliance, or delete the logs. Now, obviously in security, we're going to retain those logs, and so we don't want to pull the log group down whenever we delete the stack. However, if we need to put that control back in place and we use the same name, we're going to end up with conflicts because the log group is going to already exist. The Lambda function in the CDK and the log retention policy uses the custom resource to handle that for you so that you can retain the logs and reuse them whenever you deploy your function again. That's great functionality, but again, if you're in security and you're seeing custom resources show up that you're not aware of, it can be concerning. So it's just something to note that even touching individual properties can pull entire custom resources into your account. And if you're not aware, a custom resource is itself a Lambda function which has permissions and will execute on every CloudFormation stack update. The JSII errors are not always straightforward. So as mentioned, the CDK is available in multiple languages, and it uses uses JSII in order to convert to those multiple languages. However, if you choose to adopt anything other than TypeScript and you run into exceptions whenever synthesizing or deploying your stack, it will additionally add JSII errors into your output, and that can be difficult to debug. And we want to reduce the friction on the Guardrail engineer's side. They should only be dealing with the business logic, that event pattern, and the Lambda function. And if they have to dig through stack traces because of a bad release, that can be really annoying. In addition, it's one more point to debug whenever you do have these problems. If the infrastructure team is introducing a new feature and they're having some issues with it or any exceptions are occurring, you have to look, is it an issue with the configuration? Is it the CDK itself? Or is it JSII? It's rarely JSII, but sometimes it is. And so that can make debugging a lot harder. And the last part is that it's really hard to extend the command line interface of the CDK. So in the second example, where we'd abstracted the CDK out entirely, we wrapped it in a command line interface to abstract away the CDK calls. And at the bottom of the first file, we called app.synth. Now that was calling out to CDK's own synth method, and that created the stack for us. For the example, that's really great because we can synthesize the stack and show it. But unfortunately, other commands like deploy aren't exposed through the CDK. Now you can still re-implement them, and they're not terribly difficult to do, but it's not something that's made publicly available on the interfaces exposed from CDK. So whenever you go to implement those other methods, you will have to copy some internal tools or internal functions from the CDK. There is an RFC out. They're working on exposing more of these interfaces to users, but for now, it's still something that you have to deal with. In the end, the CDK brought us a lot of joy. We reduced our time to Guardrail from 2 weeks down to less than 2 days. And when I say 2 weeks, I mean that's 2 weeks for a seasoned control engineer who has written several of these guardrails or controls, and it's going to only take them 2 weeks to implement a new one. Now we have a fairly consistent 2 days. Whether you're a brand new engineer to our team, or you're an engineer who's been working on these for months, or you're someone from outside of our team, you can come in and look at these very few files and reason about them. And it's fairly self-documenting, although we do obviously provide lots of good documentation for onboarding, which is easier to maintain because we have less code. We're able to distribute these patterns to multiple teams. So I just mentioned, whether you're outside the team or inside the team, you can adopt this. This pattern is great for security controls, but it's also great for any other infrastructure that you need to repeat over and over again. It's always good to abstract away the CDK and let the engineers who are trying to focus on that business logic focus on just the few files that are important to them, and you can take this pattern beyond security controls. We've also reduced the knowledge silos. So when you've got 88 files and thousands of lines, there's only so many engineers who are going to know about specific files. As Richard mentioned earlier, files get copied around. Engineers don't know what's already available within the package. They might add new files. So by centralizing all of this and reducing the amount of code and increasing the documentation, we're able to reduce those knowledge silos and make sure that everyone can come in and know exactly what to do whenever they see a new control. We've also been able to evolve the configuration over time to support multiple patterns. And at this point, we're up to 7. We'll probably have more in the future as new requirements come in. But again, changing to the configuration file allowed us to version it and validate it. And that means that we can look for conflicting parameters or validate that values are correct. And that has allowed us to extend that configuration over time to support more of these patterns. In the future, we hope to open source this, and we'd like for you to look out for a blog post from City if we do. Thank you for attending FSI 305, Scaling Security Controls at City.